Hello everyone, welcome to the Market Virtual. Hope you are doing good. Today I'm going to continue with chapter number 4, that is processor architecture. So I'm going to continue with the next topic, that is pipelining. So today's topic is pipelining. But before that, let's take a quick review of the previous class, that is yesterday's class, what we have covered in the last class. So let's take a quick review. In the last class, we discussed about the sequential Y86 implementation. That is how Y86 implemented in the computer architecture. That is sequential Y86 implementation. There are three topics which we have covered in the yesterday's class. One is Y86 introduction, another one is Y86 ISA, then Y86 implementation. So let's start with the introduction. We have discussed about the introduction, that is Y86 is a new version of the subset of the IA32. That is, it is an advanced version of the IA32 architecture. It has a complicated or too many instructions with an complicated encoding. So that encoding part in this Y86 is very complicated. And there are too many addressing modes available in IA or Y86. And it has means Y86 has 8 general purpose 32-bit registers, 1 program counter, that is PC, 3 condition codes, that is ZF, sign and overflow. Next, there are 12 types of instructions. So the Y86 contains 8 general purpose registers, PC, 3 condition codes and 12 types of instructions. Next is Y86 ISA. Till now we have covered about the Y86 introduction. Now next topic is Y86 ISA. That is, we have covered about the Y86 ISA. This is these are the 32-bit registers. They are 32-bit registers that is used, and there are 8 registers that is used, that is from 0 to 7, and there are each register is of 32 bits each, that is from 0 to 7 and each of the 32 bits. So it contains 2 par 32 bits we have discussed. Then we have discussed about the multiple instruction types that is used in Y86 implementation. One of the instruction type is register memory transfer, that is how to transfer from the one memory to the another, from one register to the another, from one memory to the register, from one register to the memory. So there are 4 methods: from memory to memory, from register to register, from register to memory, and vice versa, from memory to the register. These are the multiple examples. Then another instruction is that data transfer instruction. That is how we can move the data from one register to the another or from one memory to the another. These are the registers. The transfer is from RA to the RB, and this is from variable or the memory or to the register. Then next one is your arithmetic instructions. There are another instruction that is known as arithmetic instruction. So there are multiple arithmetic instructions available like add L, subtract L, AND L, XOR L, mul, R, that is multiply, divide, finding the modulus. See, these are the 3 extensions that is add-on after using the arithmetic instruction. That also includes logical instruction. And 3 more are multiply, divide, modulus. Then next instruction is unconditional jump. That is how we jump from one location to the another location unconditionally. Then next one is your conditional jump. That is how we jump from one location to another conditionally. Conditionally means on the basis of condition we jump from one location to another location. Like the condition is that jump or find or jump to the destination if the last result is greater than equals to 0. Jump to the location, jump to the destination if the result is less than 0. Equals to 0, not equals to 0, greater than 0, and the greater than equals to 0. Next is your conditional move. Then we also talked about the stack, that is how stack is used in Y86 implementation. What are the terms that is stored in Y86 implementation in stack? That uses LIFO. that is last in, first out. So these are the multiple runtime stack variables, that is argument 1, argument 2, argument 3, return address, local data and local data for ESP. These are the multiple next instruction, that is procedure calls. That is whenever we divide the main function into the sub parts, into the multiple parts, that is known as procedure. And when we call the procedure, when we invoke the procedure, when we invoke sub program and return any value, that is known as procedure calls and return support. There are multiple instructions that is available in procedure, like CALL, RET, push, pop. Push is used for inserting, pop is used for removing. Other instructions are hold, that is used for stopping the execution, and NOP, that is of no use, but hold is used for stopping the execution for the time being. This is a C example. We have discussed about the C example. Here start is an array. Start is an array variable that returns the value int and that contains the value 4, 7, 8, 9, 12, 11. And we use the function, that is sum function, and variables are sum, count, str. Str is a pointer variable that stores the address of the next variable, that is start variable. And there is a while loop that counts the number of iterations, or it execute till the number becomes, or the count becomes 6. So it starts from 0 and ending with the 6, or it starts from 6 ending with 0 anyway. Next, we have also studied how we have compiled with the help of assembly language. That is how we have written for the Y86. Then Y86 implementation. Then we have also discussed about the Y86 implementation. That is how Y86 implemented in computer architecture. We have covered about the two terms, that is introduction and ISA. Next part is the implementation. These slides say what are the requirements, or what we require for implementing the Y86 ISA. So we require registers, we require memory, we require ALU, PC. PC is program counter and so many things, but these are the basic things like memory, ALU, PC, registers. PC is program counter that uses or that stores the instruction or the address of the next instruction. And along with that, we also require combinational or combinatorial logic like AND gate, OR gate, NOT gate, multiplexers. And how we describe and how we use the combination logic by using the HCL, that is hardware control language. And we use Java language for implementation of the Y86. So the programming language used over here is Java language. Then this is the most important part, how we are implemented, or how we execute the execution, or how we execute the multiple instructions into 6 stages. What are the 6 stages? Fetch, decode, execute, memory, write back, PC update. So these are the 6 stages that is available. First one is known as fetch, that is use of fetching. Then decoding means read from the register. Then execute the instruction means executing or performing the operations that is done by the ALU. Then reads the data from the memory or store the data from the memory, that is next phase, that is memory. Next one is the write back, means storing the value or writing the values into the registers. Then PC update means how to store the new PC value or how to update the PC's value, that is your program counter's value. These are the 6 stages that is available during the instruction execution. This is your next example, that is for fetch, decode, execute, memory, write back, PC update. Then we also discuss about the implementation details, that is how we are using from one part to the another part, that is your implementation details. These are the some multiple methods like read write memory, that is mem.read, mem.read integers, read write register files. Then we also talked about the read write stage registers. And what is the difference between the Y86 registers and the Y86 state registers, that is a part of the CPU. We also discussed about the SEQ, that is sequential hardware. means what are the terms available in the hardware of the sequential. So there are multiple boxes, multiple colored boxes that are differentiated or that is differentiated between the different elements of the SEQ. So light gray boxes uses or used for the memories ALU. Memories means it may be primary memory, it may be secondary memory, and ALU means that is used for execution. That is arithmetic and logical unit. And the dark gray boxes are used for describing or description of the HCL, that is hardware control language. And white oval is used for only signals, that is how signal are passing and what are the signals that is available for SEQ hardware implementation. Then thin lines are used for 4 to 8 bit values and dotted lines are of 1 bit value or shows the 1 bit value. Then next shows fetch cycle, that is how we are fetching or how we fetch from the memory, that is known as the fetch cycle, that contains multiple blocks like PC, instruction memory, split, alignment. Then we also talked about the fetch control logic, that is how we control or how we are using the control logic in the fetch cycle. Next one is your decode cycle. We also discussed how to use the decode cycle in assembly language so that we read the files, they read the registers, write into the register and controls the logic. So that's all for yesterday's session. Today I'm going to continue with the next topic, that is as per your book, that is pipeline. Today there is some network problem. This is your next topic, that is general principles of pipelining. That is how we are using the pipelining, what is the hardware concept of pipelining, what is the software used in the pipelining, and what are the models or the types of hazards that is available in pipelining, and what are the types of pipelining. So these are the multiple terms or multiple concepts that are used in the pipelining. So let's take with the help of the PPT so that you can understand in a better way. So that is the main target of using the PPTs. That is your general purpose of pipelining. That is what is pipelining, how it is used, what are the concepts used, that is general principles of outline. So let's start. Chapter 4 continued, that is processor architecture. The topic is pipelining. So first of all, what is a pipelining? Pipelining is used by virtually all modern microprocessors to enhance performance, means to increase the performance by overlapping the execution of instructions. How to overlap? That is done by the pipelining. A common phenomenon for a pipelining is a factory assembly line. That is, we are using the line-by-line sequence for executing the pipelining method. So first one says it is used by all the modern microprocessors or all the microprocessor or computer CPU to enhance or to increase the performance by overlapping. Overlapping means by executing or by increasing the executions of the instructions. So pipelining is used for increase the performance, increases the efficiency. A common phenomenon or common analog for a pipeline is a factory assembly line. Assume there are 3 stages. In factories, assume there are 3 stages like welding, painting, polishing. So first of all, welding is done, then painting is done, and then after that a finishing is given to the factory assembly line so that they can be available in the assembly part. For simplicity, assume that each task takes 1 hour. So this is the example, that is each task takes 1 hour. If a single person were to work on the product, it will take 3 hours to produce one product. So because each there are three parts, that is welding, painting, polishing. So if a single person is available for 1 hour, so these take 3 hours to complete the or produce the one finished product. If we had 3 people, one person could work on each stage. That is, one is used for welding, one is used for finishing, and one is used for painting. Then their task will be completed upon they could pass their product on to the next person. It depends on the person. Suppose a person is using or doing the welding, then it must pass to the next person that is doing the painting, and then that person pass to the next person that is doing the polishing. So it depends on the person to person, that is how person are using or how person pass their product to the next person. Since each stage takes 1 hour, there will be no waiting. Suppose if a person is passing to the next person in a no mean of time or even no wastage of time, that is within whenever a process is done, pass to the next person. Another process is done, pass to the next person. Another process is done, pass to the next person. So that takes only 1 hour for completing the execution. Then next point says we can then produce one product per hour assuming the assembly line has been filled. Assume that 3 persons are waiting or 3 persons are assigning their multiple tasks for 1 hour each. So it takes 1 hour for completing the task. One person is doing the welding, one person is doing the painting, one person is doing the polishing. Next, what are the characteristics or how we can characterize pipelining? First of all, the different version or different characterization of pipelining is, first one is your hardware or software implementation. That is, pipelining can be implemented. It may be or it can be implemented in either software or hardware. So there are two parts of implementation, using the hardware and using the software. If you are using the hardware, that is known as hardware pipeline. And if you are using the software, that is known as software pipeline. Next, large or small scale. So pipelining is also done in multiple scales, that is on a large level or in a small level. This says stations in a pipelining can range from simplistic, powerful, and the pipelining can range from a short to the low. That is your large or small scale. Then there are again next part of pipelining is your synchronous or asynchronous flow. A synchronous pipelining operates like an assembly line. At a given time, each station is processing some amount of information. So there is a synchronization between the persons. If a person is using the welding, then he or she must coordinate with the next person that is doing the painting. And that painting person is also coordinated with the next person that is doing the polishing. So there is a synchronization among the different persons that is doing the multiple tasks in the pipelining. So synchronous pipeline means there is a synchronization between the different persons who is doing the multiple tasks, who is doing one task for the pipeline. In the same way, asynchronous pipeline allows a station to forward information at any point of time. Because there is no synchronization, they can transfer their data or they can transfer their information or forward their information at any point of time. Then next category is buffered or unbuffered flow. That is how we are doing the buffering. That is how one part of the stage or one stage of the pipelining sends data directly to the another one, or a buffer is placed between each pair of devices. That is how one stage or how one part of the pipelining sends the data directly to the another one. That is, there is no intermediate between the two persons that is using the or that is doing the pipelining procedure. Suppose one is doing the welding part, one is doing the painting part. So there is no buffering, there is no intermediate between them. There is a direct communication between the person to person. That is known as buffered pipeline. Then next category is your finite chunks or continuous bit streams. That is, the digital information that passes through a pipeline can consist of a sequence or small data items or an arbitrary long bit stream. That is, we can divide the pipelining, or we can divide the pipelining task into multiple chunks or the finite chunks. Chunks means parts, finite means there is an exact figure or the continuous bit stream. We can also divide the pipelining into bit stream like zeros and ones. That is in digital format. Then next part is your next category is your automatic data feed or manual data feed. So next category or the sixth category is automatic data feed. That is, or it in pipelining, automatic data is feeding into the memory. Automatic data is feeding into the pipeline. This says some implementation of pipelining uses a separate mechanism or uses a different mechanism to move the information, and other implementation requires each stage to participate in moving information. So there are multiple implementations multiple parts of the implementation that is used by the pipelining. So it may be implemented using the separate mechanism or using the separate memory information, using the separate implementation that require each stage to implement or participate in the moving information. So if they are using the automatic part, so there is a separate mechanism. If they are using the manual part, they are using the moving information, they are using the manual way, that is one person is passing the next person. That is your manual information or the manual feed, that is passing from one part to the another part, or one person to another part, another person manually. Next is again what is pipelining. This is pipelining. This is the one of the example. Again we are talking about the pipelining. So this is a technique that is used in advanced microprocessor. There are different categories of microprocessor CPU. So it is a technique that is used in the computer architecture or used by the advanced microprocessor, where the microprocessor begins executing a second instruction before the first instruction has been completed. So there is a multi-instruction that is executing, that is done by the, or that is executing by the pipelining. As I said you the example, one person is doing the welding, one person is doing the painting, one person is doing the polishing at the same time. So the task is completed in a very quick fashion, very quick manner. That is technique that is used in advanced microprocessor, that is known as pipeline. Next is a pipelining is a series of stages. That is, a pipelining contains multiple stages where some task is done at each stage. As I told you, the work is not finished until it has passed through all the stages. Means if a welding part is done and the painting part is pending, so it is not that, it is not sure that the work is finished, but not. If all the persons are doing the task at the same time, at their given time, then only the instruction is finished, then only the part of the pipelining is finished. Then next point says, with pipelining, the computer architecture allows the next instruction to be fetched while the processor is performing arithmetic operations. As I told you, if one instruction is executed, then the processor is performing the arithmetic instruction or fetch from the arithmetic instruction to perform the arithmetic operation, holding them in a buffer close to the buffer until each instruction operation can perform. So with the help of pipelining, we can use the buffer that is close to the processor so that each instruction operation can be performed, that is arithmetic instructions can be performed on the computer architecture. This is the example. Next example. One example is your polishing and welding, finishing. Like next is a laundry example. This is a laundry example where you can wash the clothes, that is your laundry. So there are few names, that is 4 names: Anne, Brian, Kathy, Dave. Each one of one load of clothes to wash, dry and fold. So they have a one load of clothes. They want to wash, they want to dry and they want to fold them. Washer takes 30 minutes, dryer takes 40 minutes and folder takes 20 minutes. So these are the 3 tasks that is done in sequence way. One is N is using the washer, for example, Dave is using the dryer, Wayne is using the folder at the same time. So that is done by the, or that is the example of the pipelining. So this is the 6 p.m. at the starting, 11 p.m. in the midnight. Task order, that is A, B, C, D. A is using the 30 to 40 minutes for the, this is used for 30-minute washer. This is next 10 minutes is used for dry. B is used for 30 and 40. Same way, C is used for 30 and 40, and D is used for 30 and 40. There are multiple time intervals: 30, 40, 20, 30, 40, 20, 30, 40. In the same way, they are using also the 20 minutes for 20 minutes for folder or for folding the clothes. Sequentially, laundry takes 6 hours for 4 loads. So it takes 6 hours because first of all A, then B, C, D. So it takes 4 hours or 6 hours for 4 loads. 6 hours means from 6 to 12. That is from 6 hours. If they have learned pipelining, how long would laundry take? As I told you, laundry places along with one by one, that is one instruction is executing, along with that next instruction is also executing. So this is the best example. If they, all the persons have knowledge of the laundry or knowledge of the pipelining, so how much or how long would laundry take, or what is the time that is saved for the person? Now let's see. Start work as soon as possible. That is, if A is using the 40 minutes for this, that is 40 minutes for dry, that at the same time B is using the 30 minutes out of the 40 minutes for the washer. In the same way, A is using the 40 minutes, 20 minutes for folder in the 40 minutes also. So they are, as you see, they are both using, A and B both using the same timing. In the same way, A and B also using the both timing. One is using for washer, one is using for dry. One is using for folder and one is using for dry. So they are executing multiple tasks at the multiple time along with their time. So because 40 is more than the 20 minutes, 20 minutes is used for folding. This is the best example. If there is no laundry, pipelining laundry takes only 3.5 hours. That is from 6 p.m. to the 9.5 p.m. This is your 9.5. That is 9:30 p.m. That is your 9:30 p.m. Right, so it is till 9:30. That is, it takes 9:30 3.5 hours for 4 loads. 4 loads means A, B, C, D. Next, pipelining lessons. Pipelining does not help latency of single task. Latency means it does not wait for the single task. It helps throughput of the entire workload. Means it is not effective for the single instruction or for the single task, but it is effective for the multiple tasks. So that task will be completed on the time. So that task will complete on the time after executing or after finishing the instructions. Then next point says pipelining rate limited by the slowest pipelining stage. Multiple tasks operating simultaneously. This is the main point. Then multiple tasks are operating or multiple tasks are operating at the simultaneously stage on the simultaneously. Then potential speed up equals to number of pipe stages. That is, depends on the number of pipe it is used in pipelining. Then next one is your unbalanced length of the pipe stages reduces speed up. Then time to fill pipeline and the time to drain it reduces speed up. Next is your how pipelining works. So till now we have covered what is pipelining, how we can divide the pipelining into multiple parts, what are the examples of pipelining. Next is how it works or how our pipelining works. So as you see in the example, the same task or the same process is divided into multiple segments and multiple segments can execute simultaneously. so that the main instruction or the main segment is executed at the end very efficiently and effectively. This says the pipelining is divided into multiple segments. Segment means multiple parts, and each segment can execute its operation concurrently with the other segment. As I told you, each segment or the multiple segment can execute it or execute the segments or the operations concurrently, means along with one another, side by side with the other segments. Once a segment completes an execution, once a segment completes an execution or operation, it passes the result to the next segment. Suppose I have divided the one segment into four parts. So if one segment is executing or completed the task, completes an operation, it passes to the next, that is the second segment. In the same way, it passes to the next segment, that is your third segment. In the same way, passes to the next segment, that is your fourth segment. And at last, the main segment or the main task is carried out. In the same way, it is says, once a segment completes an operation, it passes the result to the next segment in the pipeline and fetches the next operation from the preceding segment. Suppose second segment is doing something, and he or she have done the thing that is using the segment. So he or she or it passes the result to the next part and fetches the instruction from the back, that is segment number 1, to execute them. In the same way, one output is out, another input is come. One input is come, another output is down. In the same way, they can flow with each other, and at last, the main instruction, the main segment is executing or following the pipeline. Then next example is where this is the example: instruction 1, instruction 2, instruction 3, instruction 4. At last, the main instruction or the main operation is performed. There are 4 instructions: 1, 2, 3, 4. 1 is transferred the output to the 2, 2 is transferred to the 3, 3 is transferred to the 4. 4 sample instructions executed linearly. That means in a linear fashion. If one is executing, then only second is executing. If second is not executing, then the instruction is terminated over here only. It will not go to the next part, that is instruction number 3. These are the 4 pipeline instructions, that is they are using the same time, ID and IF, EX, ID, MEX. They are using the same timing. In the same way, they are using the same time. Now, next is your instruction fetch, that is IF. That is how we are using the instruction fetch and how we fetch the instruction from the memory from the pipeline. So instruction fetch means IF. It is the short form is IF. That is, instruction fetch stage is responsible for obtaining the requested instruction from the memory. That is used for fetching the instruction from the memory. That is your instructions fetch. As the name advises, instruction fetch, that is fetching the instruction from the memory. The instruction and the program counter. What is program counter? That is used for the next instruction. And if this is mentioned, which is incremented to the next instruction, are stored in the IF ID. IF is instruction fetch and the ID is your instruction decode. As used recall the last class, that is multiple stages like fetch, decode. In the same way, there are multiple phases in pipeline. So fetch is used for obtaining the requested instruction from the memory that are stored in either IF or ID pipeline as a temporary storage, so that they may be used in the next stage at the start of the next clock cycle. What is the clock cycle? Whenever we use the clock for sending the signal, that is known as the clock cycle. So whenever we use the IF or the ID, that is instruction fetch and the instruction code that is used for the storing the instructions. Next is your instruction decode that is responsible for decoding the instruction. Decoding means fetching the memory or fetching the data from the register. For decoding the instruction and sending out the various control lines to the other parts of the processor. The instruction is sent to the control unit that is responsible for controlling, where it is decoded and the registers are fetched from the memory. As I told you, decode is used for fetching from the memory. So this says ID is responsible, that is instruction decode is responsible for decoding and sending out various control signals to the other parts of the processor. Next part is your execution, that is where we can execute or where we perform the operations. As I told you in the last class, the same follow-up of the multiple stages like fetch, decode, execution, and that execution is done by the ALU, that is arithmetic and logical unit. Next, memory and input output, that is how we are storing or how we are using the storage purpose, that is how we store the data and how we retrieve the data from the memory, that is known as memory and input output, that is taking the input from the memory, storing the output to the memory. So the memory and the input output, that is MEM stage, is responsible for storing and loading the values to and from the memory. That is, to means fetching the memory or storing the data into the memory, to means storing, and the from means fetching the data from the memory. It is also responsible for input or output from the processor. Not it is essential that it is used for only storing the value from the or retrieving the or storing the values from the memory. No, it is also used for inputting and outputting from the processor also, that is your CPU. If the current execution or the instruction is not part of memory or IO type, then the result from the ALU is passed to the write back stage. So it is shown that, or if the current instruction is not a part of the or not fetched from the memory, so it is passed to the write back stage. Another one stage is your write back stage, so that it can be back or it can be returned to the back stage. So WB, that is write back, is also responsible for writing the result of a calculation with memory access or input into the register file. So it is used for return purpose or for writing purpose, that is your write back. Next is your operation timings, that is that is what is the timing or how much long multiple instructions, multiple stages can execute for how much long time. That is the operation timing. This is estimated timing for each of the stages. This is the estimated timing, not the exact timing. Like instruction fetch uses 2ns, 2 nanoseconds. Instruction decode, that is fetch cycle takes 2 nanoseconds. Decode takes only 1 nanosecond. Execution takes 2 nanoseconds. Memory and input output takes 2 nanoseconds. Write back takes 1 nanosecond. But you see this table, no one cycle or no one stage takes more than 2 nanoseconds. The maximum is your 2 nanoseconds. 2, 1, 2, 2, 1. That is your instruction fetch, decode, execution, memory, write back. Next, what are the advantages or disadvantages of pipeline? This is the most important slide. The main advantages is that more efficient use of processor. As I told you, multiple instructions are using or executing in a pipeline, in a multiple or in a simultaneously fashion. So this is the most efficient advantage, is that it is the efficient or it uses the efficient of the processor. That is more efficient use of the processor. That is processor is used more efficiently. That is done by the pipeline. This is more efficient use of the processor for executing the instruction. Then next one is your quicker time of execution. As there is a less number of instructions or multiple instructions are executed at the same time, so this takes less time or it saves the time for the instruction for the large number of instructions. So the two advantages, that efficient or the optimization of the processor and the quicker time of execution or the time saving, that is programs or the instructions are executed in a more efficient time, in a sequential time, or in a quicker time. Then disadvantage. This means pipelining involves adding hardware to the chip. So that needs, or the pipelining needs the new hardware that is adding to the chip, or that is adding for the chip, so that instructions will execute at the same time. That is, pipelining requires new hardware or the new setup for the chip. That is how we are using the pipeline. Next is your inability to continuously run the pipelining at full speed because of the pipelining hazards. Hazards means your problems. So this is your next topic. So pipelining hazard. So this is the inability or the inappropriate to continuously run the pipelining at full speed. So it is not always important that you are using the pipelining at your full speed. There is some hazard which disturb the smooth execution of the pipeline. This is your next disadvantage. So the two disadvantages or two limitations are they require new hardware, and due to the hazard, the pipelining stops very quickly. And the advantage is that more efficient use of processor and the time saving. Next, what are the pipelining hazards, or what is the pipelining hazard? Hazard means that disturb the current execution, current execution of the pipelining or current execution of any process. If I am using computer hazard, that is disturb the current execution of the computer. So hazard means that is disturbing element that is disturbing the multiple parts. If I am using pipelining hazard, so it is disturbing the pipelining. If I am using computer hazard, so it is disturbing the current execution of the computer. If I am using mobile hazard, that is the disturbing the current execution or the current flow of the mobile phone. So this says there are situations, there are conditions known as hazards that prevent the next instruction in the instruction stream from executing during its designated cycle. That is, these are the disturbing element that prevents the next instruction in the instruction stream. Instruction stream means in an instruction queue, it prevents the next instruction to execute during its designated cycle or during its assigned task or during its assigned timing. So it requests or it fetches or it prevents the instruction to be used or it prevents the next instruction to be executed during their assigned time, assigned cycle, assigned follow-up. There are three classes of hazard. There are three classes of disturbing elements: structural hazard, data hazard, branch hazard. So there are three elements that is used. That is the pipelining hazard, how structure, data, branch. Now, what is a structure hazard, what is a data hazard, and what is a branch hazard? So remember, hazards are the disturbing element which disturbs the instruction to be executed. So the first one is your structure hazard. This says this resources conflict when the hardware cannot support all possible combination of instructions simultaneously. So structure hazard means there is a difficulty or there is a disturbances or there is a disturbances in the structure, that is a hardware element. There is disturbances in the hardware element that does not support the combination of instructions or that multiple instruction cannot execute simultaneously due to the resource problem, due to the hardware problem, because the hardware cannot support the software. So as the name implies, structure hazard. So there is some disturbances or there is a disturbance element in the structure, that is a structure hazard. Next, data hazard means there is a disturbing element in the data, that is data is not fetched or not write, not read from the memory. This says an instruction depends on the result of the previous instruction. Data hazard means the previous output is not coming, so the next instruction will not execute, that is known as data hazard. That is on data. Next, branch hazard, that instructions change the PC. Then next hazard is branch hazard. This is the condition, this is a disturbing element, then the whole branch or the full branch is removed or the change, that is your branch hazard. There are three hazards, that is the disturbing element that is available in pipelining. We will discuss it like in serial order, that is one by one. But before this, let's take a quick break or the 5 to 10 minutes break and then come back and start with your these topics, that is your hazard, and then for the next topics. So let's take 5 to 10 minutes. Now let's start with your pipelining hazards. So first one is your structure hazard. As a name advice, on the basis of structure, there is some disturbances, that is known as structure hazard. This says some pipelining processors have shared a single memory pipeline for data and instructions. Means they uses only the single pipeline for the single line for the single instruction. That uses both the memory pipeline for data and the instruction. That is, the single pipeline is used for data and the single pipeline is used for instructions. This is your structure hazard example. Memory data fetches or fetch requires an Fi and Fo. This is S1, S2, S3, S4, S5. This is a fetch instruction, that is fetch cycle, decode, fetch operand, execution cycle, and write operand. These are the multiple instructions, multiple fetch cycle that is uses, and these are the timing, that is S1 takes 9 minutes or the 9 bytes, S2 takes 8 minutes or the 8 bytes, 7, 6, 5. Then next one is that to solve this hazard, we stall the pipeline until the resource is free. Means we uses the concept that I will discuss in the later slides with after 2 or 3 slides. That is what is stall. Means to resolve the structure hazard, we use the concept, we invent the concept that is known as stall, that requires the pipeline, means stalling the pipelining until the resource is free. That is stalling the pipelining. A stall is commonly known as pipeline bubble. This is all the another name of for stall is pipelining bubble, since it floats through the pipeline, taking space but carry no useful work. That is, it floats, it works through the pipelining, taking the space in the memory but carry no useful work. This is your structure cycle, that is your stall that is used for the pipelining, that is 1, 2, 3, 4. Using extra space, using extra space, extra space, extra space. This is your S, 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 S. Next is your data hazard. That is, this is a hazard, that is how the disturbing element affects the structure of the pipelining. That is your structure hazard. In the same way, next is your data hazard. That is how the disturbing element or the data elements are disturbed or disturbed with the pipelining or in the pipeline. But before this, let's take a quick review of your book, what we have covered or what we have discussed according to the book. This is general principles of pipelining, that is how we are using the pipelining. This is the example or the diagram for the pipelining, that is how we are implemented using the hardware, using the pipelining diagram, that is how we are using and how we are using the pipelining methods. These are the computational pipeline, that is what are the requirements or what are the bytes required for the pipelinings. This is the formula, that is throughput means the output equals to 1 instruction upon 20 plus 300 picoseconds into 1000 picoseconds upon 1 nanosecond. That is approximately, this sign is used for approximately, that is approximately equals to 3.12 GIPS. That is giga instructions per second. These are the examples for the pipelining. This is 3-stage pipeline computed hardware, that is ABC, 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 as I told you with that for PPTs. These are the pipelining operations. ABC, ABC, ABC. A takes 0 to 120. B and A both share the timing, that is your three-stage pipelining, that is, three instructions are executing at the same time depending upon the clock signal. So depending upon the clock signal it is used, that this is the rising edge of the clock signal controls the movement of instructions from one pipeline stage to the another. So when the A forwards the data to the B process the data, it forwards the data to the C. In the same way, A process, B process, C process, A process, B process, C process. Then at last the final stage is over and the final output and the final instruction will carry out. This is your three-stage pipelining. Why three stage? Because there are three elements, there are three person or the three stages are involved in the pipeline. Then what are the limitations? The figure 33 shows an ideal pipeline system in which we are able to divide the computation into three independent stages like A, B and C, each requiring 1/3 of the time required by the original logic. Means how we are using and how we use the multiple computational tasks and how we divide the task or the instruction task into the three divisions so that two persons can execute in the half stage or two persons can execute the instruction at the same time continuously or simultaneously. Unfortunately, other factors often arise the diminishing of the pipelining. The three limitations are, as I told you, there is new hardware used. This is a new hardware that is used, and the another one is there is a hazard, pipelining hazard that disturbs the elements. This is the limitation of pipelining due to the non-uniform stage delay. So there is a delay in the stage uniforms. Next, diminishing returns of deep pipelining. That is the another example. That is how we return the deep pipelining. Next, pipelining a system with feedback. That is how a feedback is given, and how for a system execution with the IA32 or Y86, we require potential dependency between the instruction that is required for the pipelining instruction. This says there is a data dependency. As I told you, if the welding, for the previous example, if the welding done is not over, painting is not done, because before painting, welding is mandatory. In the same way, before finishing, before polishing, a painting is required. So these are all related and these are all dependent between each other, and these cannot be carry forward or executing until the output will come from the previous stage, and the output of the same stage is given to the next stage, that is to the next part. For example, painting person is given assign the task to the polishing person. These are the examples. The IR move instruction stores its result in the EAX, which then must be read by the ADDL instruction, that is line 2, and this instruction stores its results in the EBX. So first of all, one instruction is executed and stores the output in EAX. Then next instruction is executed and stores the output in EBX. Then this instruction stores its result in the EBX, second one, which must then be read by the move1, that is your third instruction. So these are all instructions that is carried forward or that is used line by line, that is dependent on the one another, that is your data dependency. These are the limitations, or due to the logical dependency, one value or the one instruction depends on the another instruction. Next is your pipeline Y86 implementation. But before that, let's take a quick review of your PPTs. Next is your data hazard, that is how hazard or how disturbing element or the data will be affected by the disturbing element. So there are multiple few data hazards. One is your add. This is your data hazard. R2 plus R3 means the both values are added and stored in the R1. R1 is subtracted from the R5 and storing the result in R4, that is subtract. Performing the add operation between the register, that is first of all storing the output or moving the output from the R1 to the R6 and then compare the R1, R6 and the R7 by using the AND operation. Means finding the AND operation or multiplication between R6 and the R7. So that is the main target. So first of all, move the content for the from the R1 to the R6. So the output is available in the R6. Then finding the R6 and the R7 AND operation. That is finding the AND operation between the R6 and the R7. That is your finding the AND operation means multiply the values. AND operation follows the output is 1 whenever both the inputs are true. That is both the inputs are 1. That is your AND operation. Next is your OR operation. In the same way, we are also performing, or the hazard is that if they are performing OR operation. This is your example. In the same way, they are performing the XOR operation, but on different values. They depend on the different values. R1, R10 is depending on the R1, that is your data hazard. R8 is depending on the R1, that is your data hazard. Means they are not related with each other. They are dependent on the another person, on another register. That is R1 is dependent on R2 plus R3. R4 is dependent on R1 and R5. This is your data hazard diagram. First one is S1, that is fetch, decode, fetch operand, execute, write operand. This is your time level, that is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The 5 will use the 3 and the 3. That is third operation of the next line, third operation of the next line. F4 means fetch data value. WO means write to the data or write the operand, that is store the executed value. Delay load approach inserts a no operation instruction to avoid the data conflict. That is your data hazard. First of all, add, that is R1 plus R3 is going to the R1, R1 minus R5, R4, the same operation. There is no operation between the add and the subtract. So that there is a delay between the add and the subtract. That is, add is passing the output, or as is add is giving the output, but subtract is not able to take the output. Or in other terms, add is not able to give the output and the sub is able to, or subtract is able to take the input. So there is some disturbances in the data, that is known as data conflict. That requires no operation instruction to avoid the data conflict. This is the data conflict. There is a no operation. Directly 5 is going to the third instruction at the third level. It can be further solved. Means what is the solution? It can be solved by using the simple hardware technique known as forwarding. So it can be used, or it can be solved. The solution of the data hazard problem is forwarding, that is bypassing or short circuiting the result, that is bypass the result to the next person. In the same way, bypass or forward the result to the next person, next person, forward the result to the next person until the persons or the full instruction will not carry out. That is your forwarding part. Next point says the insight in forwarding is that the result is not really needed by the subtract until the add execute completely. As I told you, there is a no operation between the add and subtract. The solution is that the insight in forwarding is that the result is not really needed by the sub. It is not mandatory that the result of add is always required by the subtract. No, until the add executes completely, because the subtract requires the input that is full and final, that is not half. So it is not mandatory, or it is not really needed by the subtract until the add executes simultaneously. If the forwarding hardware detects that the previous ALU operation has written to the register corresponding to a source file for the current ALU operation, control logic selects the result in ALU instead of the or from the memory. That is, they are using the ALU operations and results are stored in the ALU instead of the memory, because ALU performs the operation, ALU fetches the instructions, ALU performs the arithmetic and logical operations. So they are using the memory. If there is a concept or there is a delay from the memory, so it uses only ALU, that is arithmetic and logical unit, for storing the data also. That is a solution for this problem. This is only no operation for runtime, that is 4 is required for the 3, that is 4 is related to the 3. Now, next hazard is your branch hazard, that is how we are using or how we are used the branch hazard. So first one is your data hazard, next one is your, this is your data hazard, then structure hazard, and then last one is your branch hazard. That what is the use or what is the motto of the branch hazard and what is branch hazard? There are 4 schemes to handle the branch hazard. But first of all, what is branch hazard? Yeah, this is the branch hazard. For handle or the solution is next thing. First of all, uses the concept or understand the concept, that is what is branch hazard. Branch hazard can cause a greater performance loss for pipelining. So this is one of the main, or this is one of the enhanced, or this is one of the drastic hazard that is available in pipelining. This adversely affects the outcome of the instruction. This causes a greater performance loss for pipelines. When a branch instruction is executed, it may or may not change the PC. So if when a branch instruction or when a branch output or the branch instruction is executed, it may or may not change the PC. If a branch changes the PC to its target address, it is taken at the branch, otherwise it is untaken. So if the PC or the branch changes the PC, that is a program counter. If the branch instruction changes the address of the next instruction, that is your program counter instruction, so it is known as the taken instruction, otherwise it is known as the untaken instruction or untaken branch. So there are 2 types of branches, taken and untaken. Taken is used for PC changes and untaken is used for not changing the PC's values. There are 4 schemes or there are 4 methods to handle or to remove the data hazards. One is your freeze scheme, that is how to freeze the scheme or how to freeze the data values. Next one is your predict untaken scheme. Next one is your predict taken scheme. Next one is your delete branch. So there are 4 types of solutions. There are 4 schemes that is used to handle the branch hazard. Freeze scheme means freezing the values or freezing the data so that it will not affect the PC's value. Freezing means that is storing the value so that it will not affect the branch values or it will not affect the another value. That is your freeze scheme. Next one is your predict untaken scheme, that is only predict the values for the untaken hazard. And next one is your predict taken scheme, that is only taking the value of the or only predict the value for the taken scheme, that is take for the next part. Then next is your delete branch. So these are the 4 techniques that is used to handle the branch hazard. Now again, what is data hazard? That uses the instruction uses the result of the previous action and data will not arrive on time, that is known as data hazard. Next, control hazard, that is the location of an instruction depends on the previous instruction, that is your control hazard, that is one location is not related to the next instruction or the next instruction. Next, structure hazard, that is the structures are different, 2 instructions do not use the same resource, that is your structure hazard. This is the example for data hazard, IF, ID, EX, as I told you, subtract, store the output. Now, stalling. Stalling is used for removing or the method for implementing or removing the which hazard? Structure hazard. So stalling involves, now what is stalling? That is stalling involves halting the flow of instruction, means stopping the flow of instruction for the time being until the required result is ready to be used. So the stalling is one of the important concepts that is used to hold or that is used to stop the flow of instructions that will until the required result is ready to be used. That is your stalling. Means stopping the values or stopping the flow of instructions until the required result is ready to be used. However, stalling wastes processor time. Why it wastes processor time? Because it holds or it stops the different flows of instructions. So the instructions will not carried out and they will stop for a moment until the result is ready to be used. For example, the result of the instruction will not arrive at on time. So the next instruction will wait for a long time. That is a long waiting time that is not available or that is not suitable for the instruction or that is not suitable for the pipelining. So it's wastes the processor time, that is the CPU time by doing nothing while waiting for the result. It waits for the result but does not nothing. So it wastes the timing for the processor. This is stall that is waiting for the next, waiting for the timing or waiting for the result. This is also waiting for the result. Waiting for the result means there are three stall, that is there are three waiting stage or there are three stalls that is available between the add and the subtract. This is the addition on the R1, R2 and the R3. This is subtraction on the R4, R1 and R5. Next, what are the types of pipelining? Here is the pipeline. Now the next topic is the types of pipelining. Means what are the categories? As we discussed about the category, they are the detailed category. The brief category or the brief categorization is pipelining is software pipelining and hardware pipelining. So the software pipelining can handle or the software pipelining handles complex instructions. That is, it handles only the complex calculations or complex instructions. Software pipelining allows the program to be reused. So it allows the multiple programs to be reused again and again when it is required. That is the software pipelining. Next, hardware pipelining. It helps the designer to manage the complexity. Means to manage the complex instructions, the complex tasks that can be divided into the smaller and more manageable pieces. That is the next pipelining, that is hardware pipeline. So it normally says or it wants to say that whenever we use the complex task that is divided into smaller and more manageable pieces, that is done by that is known as the hardware pipeline. Next point says hardware pipelining offers higher performance. Why it offers higher performance? Because every processor, every CPU depends on the hardware elements, that is CU, memory unit, ALU. So it is very necessary for the pipelining or it is very necessary in computer system to use the pipelining that offers higher performance. That is the performance for the pipelining is increased whenever we use the hardware pipeline. So the main categories of pipelining are software pipelining and hardware pipelining. Software is used to handle complex calculations, allows the program, and hardware pipelining is used to manage the complexity and for giving the or for using the or offering the high performance. That is the hardware pipelining. Next, types of hardware pipelining. There is no category or there is no advanced or the detailed category of the software pipelining, but only for the hardware pipeline. This says instruction pipeline. An instruction pipeline is very similar to the malfunctioning or the malfunctioning assembly line. The first step or the first stage receives some parts, performs its task, and passes the result to the next task. So what is the or how the type hardware pipelining works? So first of all, in first stage, it takes some part, that is the sub program of the or the sub part of the main task, perform the task, perform the assembly task, and passes the result to the next stage. So this is your first stage. Then second stage takes the partially assembled product, that is the output of the first stage, So it takes the output of the first stage, assemble the product from the first stage, perform the task, and passes the result to the next, or passes the output to the third stage. So these are the two stages. Means first of all, take some parts, process them, give the output. Second step, take the partial assembled product, take the output from the first part, add the new part. If there is a requirement, perform the task and passes to the next stage, that is your third stage. Then third stage does the work, passing the result to the last stage, which completes the task and output it result. So there are four stages: 1, 2, 3, and final. First stage takes the task, process, pass to the next stage. Second stage, process the task that is available from the first stage along with the adding the new task for the new product. Then process the task and then giving to the next stage. In the same way, third stage does the task, passing the result to the next stage, and then last stage, that is your final stage, complete the task, perform the operation by using the ALU, that is arithmetic and logical operations, logical unit, and then gives the output or gives the result to the at the final stage. This is one of the type that is known as instruction pipeline. That is, instructions are executed in a pipelining. That is your instruction pipeline. Next, data pipelining, that is used to pass the data. That is used to pass the data from one stage to the another. So instruction pipeline is used to pass the instruction from one place to another. Data pipeline is used to pass the instruction data from one stage to the another. That is from one instruction to the another instruction. It can also divide it into two parts, which that is data pipeline is divided into two categories. One is your data conflicts and branch conflicts. So now there is an explanation of the data and the branch conflicts. This says when the current instruction changes a register, that is the next one needed, that then the data conflicts happen. So whenever the data conflict changes the register, change from one register to the another register, that is the next instruction to be executed, that is the data will change, that is known as the data conflict. Then when the current instruction makes a jump means makes a branching statement, that is if else while loop, then branching conflict or the branch conflict happens. So there are two types of conflicts that is a part of the data conflict, that is your data conflict and branch conflict. So that's all for today's session. Pipelining is over. Now let's take in your book. This is pipelining implementation, that is covered in the next class. Yeah, this is covered in the next class. So I think that's all for today's session. Now, if you have any doubt, then please text that out and I will answer you. But before that, let's take a quick review of the today's class. That is what we have covered in the today's class. In today's class, our main topic is pipelining. That is a part of the chapter number 4, that is processor architecture. We started with the topic pipelining. So pipelining means executing the instructions simultaneously. In simple terms, if I say in one line, that is how we execute the multiple instruction or how multiple instructions are executed simultaneously, that is known as pipeline. So what is an pipelining? We have covered. It is used by all modern microprocessors to increase or to enhance the performance by overlapping. Overlapping means executing the multiple instructions at the same time. Overlapping means one over the another. Next, a common phenomena or the next example, common example is that there are 3 stages like welding, painting, polishing for completing the building. For completing the factory. If a single person, this is the example what we have covered, if the single person is doing the single task, then it takes 3 hours. 1 hour is used for welding, 1 hour is used for painting, 1 hour is used for finishing. But in the same way, if 3 persons are used, then it takes only 1 hour, because at the same time welding is done, at the same time painting is done, at the same time finishing or polishing is done. So this is the concept of the welding, that it saves the time. Then characterize pipelining, that is how we divide the different pipelining, that is your hardware or software implementation, that is hardware pipelining, software pipelining, large or small scale pipelining, synchronous or asynchronous pipelining, for buffered or unbuffered flow pipelining, finite chunk or continuous stream pipelining, automatic data feed or manual data feed pipeline. So these are the brief categories or the main categories of the pipeline. Then we also covered what is pipelining. That is a technique that is used in advanced microprocessors, so that processor will execute in a nanoseconds, in a few seconds. This is the example of the laundry, that 4 person wants to wash their clothes. It takes multiple minutes. If they are using different minutes, so that requires almost 90 minutes, that is 1.5 hours for completing the task. But if they are using the same timing for different processes, for different process like wash, dry, fold, that takes less time for completing the task. So this takes 90 minutes for completing the task, or 6 hours, and this takes only 3.5 hours for completing the task. Then what we have covered, this is pipelining lesson. Then next we have covered how pipelining works, that is what is the working or how pipeline works, that is how we are dividing into multiple segments, that is how multiple instructions will execute. So first of all, divide the instruction into the multiple segment, then again divide the one segment into the multiple parts, and the output of one segment is the input of another, that is your segment part. Then we have also taken the multiple example, that is how one instruction is giving the output to the next instruction, the next instruction is giving the output to the next instruction to the next instruction. These are the examples for pipeline instructions. Then we have also studied about the different stages that is available, that is fetch stage, next decode stage, execute stage, memory stage, output, write back. And we also talk about the operation timing that is required at the different stages, like 2 nanoseconds, 1 nanosecond, 2 nanoseconds, 2 nanoseconds, and write back takes 1 nanosecond. Then we also studied about the advantages and the disadvantages of the pipeline. So the main advantages of the advantage of the pipelining is that it allows efficient use of processor, that is more than one instruction are executing at the same time. Disadvantage is that the disturbance element, that is hazard, is used for in the pipelining, and it requires new hardware or the additional hardware for the pipeline. Then we also talked about the pipelining hazard, means what are the disturbing element that is available in pipelining. So there are 3 classes of hazards. One is structure, data, branch. These are the 3 hazards. So whenever there is any disturbing element or whenever there is any hardware disturbance, so that is known as structure hazard. And whenever there is any data disturbing element in passing the data, that is known as data hazard. And whenever there is any problem in branching, that is known as branch hazard. Structure hazard, data hazard. Data hazard has also 2 techniques, or also known as forwarding. This is branch hazard. These are the 4 schemes or 4 methods to remove or handle the branch hazard. That is pre-scheme, predict untaken, predict taken, delayed branch. Then we also talked about in detail about the software pipelining and the hardware pipelining. And these are the categories of the hardware pipelining. One is your instruction pipeline, then data pipeline. And the data pipeline is also divided into two parts, that is data conflict and branch conflict. So that's all for today's session. Now, if you have any doubts, then please text that out. There is one important announcement. Please listen carefully. The assignment which we have given, there are 10 questions. That is your not main assignment. That is your only class assignment. Please don't assume that this is your main assignment of the module. No, this is only the class assignment that is taken by the faculty individually. The main assignments are different ones that I will tell you when you have to do, when you have to submit, what is the criteria, what is the agenda, what is the layout, what is the format. That is a different part, but this is only a different part, that only a class assignment, that is only for checking what you have understood, what we have covered in the previous classes. So don't conflict with the main assignment with this class assignment. These are the two different class assignment and main assignment. Is that clear? I think everyone. Now, if you have any doubts, then please text the doubt. And in the next class, we have discussed about the pipeline implementation, that is pipeline, how pipeline will be implemented. So that's all for today's session. Thank you so much.
Okay.